Organic reactions are simply the making and breaking of covalent bonds. Covalent bonds are shared pairs of electrons. So breaking and making covalent bonds is movement of electron pairs. And the driving force, attraction to charge and filling outer shells. It's the attraction to charge part that I want to focus on for a minute. Electron pairs make bonds by sharing from a molecular ion, donation of a pair of electrons. This is the definition of a Lewis space, and accepting a pair of electrons. This is a definition of a Lewis acid. So you might think that we talk in terms of Lewis bases and Lewis acids, being electron pair donors that share electrons to make bonds, electron pair acceptors that accept electrons to make bonds. But we don't. This broad encompassing definition is useful at times, but in organic chemistry we use it in a very special way. We don't very often talk about Lewis bases, and when we talk about Lewis acids, we use it in a limited context. But rather we talk about nucleophiles, which are Lewis bases, and electrophiles, which are Lewis acids. It's just that the terms we use are nucleophiles and electrophiles. Let me give you a couple of examples to illustrate. Let's talk about electrophiles. Carbon-carbon double bond will react with reagents that are looking for a pair of electrons. And a good example, in fact, is a carbocation, carbon that needs a pair of electrons. The pi bond in his electron donor to form a sigma bond with that new carbon. This carbon has lost a pair of electrons as this new sigma bond was formed to this carbon. It has three things attached to it. Doesn't matter what they are right now. We talk about this carbocation as an electrophile. It's an electron pair acceptor, so it's a Lewis acid, but we don't call it Lewis acid, we call it an electrophile. Look at this one, same molecule. When treated with a strong acid, let's say HCl, we'll share that pair of pi electrons to make a new bond as this sigma bond is broken. The new product has a bond to hydrogen and a positive charge on carbon, just like above. These two reactions are conceptually identical, but we use different terms. We call this an acid. And of course, it fits the definition of a Lewis acid, the definition of a Bronsted acid, and the definition of an electrophile, except electrophiles accept a pair of electrons from carbon to make a bond with carbon. In this guy, we're calling an acid because the bond being made to carbon is with a proton. And notice that it fits the definition of a Lewis acid, but also a Bronsted acid, and we're thinking of this in terms of a Bronsted acid. A Bronsted acid is a proton donor. The reaction that happens with carbon is conceptually the same as an electrophile, but when the reaction is with a proton, we'll call it an acid. When the reaction is with something else that wants a pair of electrons from carbon, we're going to call it an electrophile. And we'll reserve the term Lewis acid for electron pair acceptors that are accepting electrons from something else, like a halide. The classic example is aluminum chloride, which has an unfilled outer shell. It needs a pair of electrons, reacting with an organic halide to take the chloride away and make a carbocation. This actually happens because aluminum gains a filled outer shell in the process, formal negative charge. That pair of electrons forms the bond with aluminum. And for this reaction to form bonds with things that don't have carbon, we're going to call these Lewis acids. Otherwise, we're going to stick with our terms electrophile, accepting a pair of electrons from carbon, acid, a proton accepting a pair of electrons from carbon,